Hello, Advanced Algebra 2. Welcome to our new unit, Unit 8, Rational Expressions and Functions. And our first concept that we're going to look at is concept 37, which is looking at inverse and direct variation relationships. And this is the foundation for rationals. So let's do an exploration. And in this exploration, you'll be able to recognize direct variation. So look at this graphic. You hang different weights from the same spring, and as the weight increases, the stretch of the spring increases in a predictable mathematical way. So if we look at the graphic, you can see a ruler over to the right in centimeters. So if you put a straight edge right across the bottom of the second spring, the bottom of the weight, you can see that that spring has stretched, measuring at the bottom of the weight 1.5 centimeters. And then the third spring, if you look across to the ruler or put a straight edge across, 3 centimeters. The fourth one, 4.5 centimeters. The fifth one, 6 centimeters. So you should notice that in each increase in weight, so 1/10 of a kilogram, the stretch of the spring increases by 1.5 centimeters. So describe the relationship between the weight x and the distance of the d the spring stretches from equilibrium. So this is A. And then explain why the spring is said to vary directly. So basically, as the weight increases, the stretch of the spring increases. Now, if we think about that mathematical relationship and we do a little number manipulation, you can see that the distance, d, of the spring divided by the weight, x, equals 15 every time. So try it real quick. 1.5 divided by 0.1 is 15. 3 divided by 0.2 is 15. So that's just a mathematical relationship that shows up. So distance of the spring divided by the weight equals 15. Or if we solve for the distance, it is 15 times that weight. So as the weight increases, the distance is 15 multiplied by the weight. This is what we call a direct variation relationship, when you have one quantity multiplied by a value and that gives you another quantity. So let's look at B. Let's estimate the values of D from the figure. Create a scatter plot on Desmos or your calculator, and then what are the characteristics of the graph? So we have those values. You can pause the video, pull up a Desmos screen, and then put in those points. So using the weight for x and the distance for y. What you'll see is that the graph, and I'll put that, so distance is y, weight is x. The graph, the points are lining up. They're linear and they are increasing. So a direct variation relationship is linear. Now for C, write an equation that represents D as a function of x. Well, I've already done that. So D equals, or y equals, 15 times x. In physics, this relationship between the distance of the spring and the weight is called Hooke's law. How would you describe Hooke's law? So I think I would say something like that Hooke's law dictates that the length of the spring is stretched. It changes or it varies directly with the weight. And again, a multiplier relationship is one that we describe as varying directly. So this is a direct variation relationship. All right, let's continue on to exploration 2. And here we're going to explore or discover an inverse variation relationship. So if you look at the table, it shows the length x in inches and the width y in inches of a rectangle, and I have a visual up there to your right. The area of the rectangle is 64. So we're going to fill in the table. So remember that x is the length. So if the length is 1 inch and you know the area has to be 64, you know that area of a rectangle is length times width. So that means that the width has to be 64. If it's 2, then the width has to be 32. If the length is 4, then the width has to be 6, and so on. So that every time we multiply that length times that width, we get 64 square inches. So describing that relationship, that means if we take and multiply together those two variables, we will get 64. So x times y equals 64. Or if I solve for one of them, let's say y, we get that y equals some number divided by x. This is an inverse relationship. So when you have one value equaling 1 over another value, or some number over another value, in math that's called an inverse relationship. Now pause the video, go to Desmos, plug in those points, and look at the characteristic of the graph. Alright, welcome back. You should have noticed that those points are creating a curve that decreases and approaches the x and the y axes, but does not touch either one of those. So part D, I've done this already in part B. Write an equation that represents y as a function of x. Well, y will equal 64 divided by x every time, and this is an inverse relationship. So let's go ahead and capture these. We've learned that two variables, x and y, show direct variation with the relationship that y equals some multiplier times x for a non-zero constant. So a needs to be some number other than 0. And then another type of variation is inverse variation. But two variables show direct variation when they are related as y equals some multiplier times x. So a set of data pairs show direct variation when y divided by x equals some constant. Now two variables show inverse variation when they are related as one of them, y equals some number value divided by the other one. So they show an inverse variation relationship when the two, if you multiply them together, you get a constant. So let's just look at each of these and classify these equations and then the data in the table. So we're going to tell whether x and y show direct variation, inverse variation, or either. So for the equations, a simple thing is to solve for one of the variables. So let's solve for y, because that's what we're used to doing, and then examine. So here we will have y equals 5 divided by x. Oh, right away, that's an inverse relationship, because one quantity equals some number divided by the other quantity. Now for b, we get y equals x minus 4. So that does not fit the pattern of inverse or direct variation. So that's a neither relationship. And then finally for c, let's multiply by 2 to solve for y. And so y equals 2 times x. This is a direct variation relationship. Notice that it's linear. And so as one variable will equal some multiplier times the other. Now let's classify data in a table. So showing whether x and y show direct variation or inverse or neither. So for direct variation, if we multiply those two x and y's together, those variables, we'll get a constant. So notice in this table we do. Every time we get negative 24. So x times y equals negative 24. If we solve for y, that equals negative 24 divided by x, which is an inverse relationship. Now let's try table B. X times y, 2, 8, 24, no, that's not direct. Y divided by x, this is, so we have a constant at first, but then 8/3, so that's no. So this table does not show either a direct or inverse variation relationship. Now we can write an inverse variation equation. So notice we've got the information that the variable x and y, variables it should be, they vary inversely. So let's write down the equation pattern that they'll fit into, which is y equals some number a divided by x. And then it says when y equals 4, x equals 3. So we'll use that information to find what our constant is, a. So we'll multiply and see that a is 12. So now we can write our inverse variation or equation that y equals 12 divided by x. So that's the answer to the first question we were posed. And then find y when x equals -2. So we will plug in -2 for x, and that will equal -6. Here's a real life situation. So the time, t in hours, that it takes a group of volunteers to build a playground varies inversely with the number of volunteers, which is n. It takes a group of 10 volunteers 8 hours to build the playground. So let's go back and use that fact that the time in relationship with the number of volunteers, n, so t to n varies inversely. So the equation pattern that will follow is t equals some constant divided by n. Now let's take that information we were given about it taking 10 volunteers 8 hours to build. So 8 equals a divided by 10, so our constant in this situation is 80. So our inverse variation equation is time equals 80 divided by the number of volunteers. So A says make a table showing the time that it would take to build the playground when the number of volunteers is 15, 20, 25, and 30. So let's set up a table. Volunteers versus time, 10, 15, 25, and 30. So plugging in 10 to our equation over on the left, t will equal 80 divided by 8, which would give us, 80 divided by 10, which gives us 8. 80 divided by 15, that's 5 1/3. So I put it in a fraction amount just to help us with time. You could write it as a decimal. 80 divided by 20, it will take 20 volunteers 4 hours. It will take 25 volunteers 3 1/5 of an hour, and 80 volunteers 2 1/3. And then probably from that point on, did I say 80 volunteers? I meant 30 volunteers. And then from then on, probably it would be too many volunteers and it would start taking more time because it would be difficult to organize all those people. So what happens to the time it takes to build the playground as the number of volunteers increase? Well, as time increases, time will decrease as the number of volunteers increase. So that is an inverse relationship. As one quantity is decreasing, the other one is increasing. All right, that concludes our concept 37, direct and inverse variation notes.